Hello, today we're talking about cyclic groups and finite cyclic groups very fast, just to explain some properties and interesting stuff for these groups. So first of all, what's a cyclic group? Let's call G a cyclic group if there exists an element so that if you repeat the operation that you define it n times, you can generate basically any element of the group. So take us a group, take one element, and repeat the operation that you define it n times. Like if I said that A is the operation that I define it for the group, I can generate this whole group by just repeating the operation. Okay, that's a cyclic group. And let's talk about a finite cyclic group. A finite cyclic group is a group that we call finite if there exists an K more or equal than 1, such that AK is equal to 1, where not 1 but E, where E is the unit element. K is called the order of the group. Okay, and yeah, let's also check that if there exists a K, then this group has order K. It's pretty damn easy to see. So I already wrote down some elements of G in terms of K. Then I can repeat the operation wherever I want. So it doesn't operate with this. So it's going to be AK plus 1, and so on. Now let's check something. AK is E since we define it. AK plus 1 is AK, A, which is EA, which is A. So this group is basically cyclic. It is cyclic, but it's finite. So the amount of elements is finite. It has order K. Nice. That's nice. So let's see an example of a finite cyclic group with a well-defined operation that we set. Here we have a group T with the operation sigma that we define it to be the association with a corner. We're going to talk this about. We're going to call these corners. Associate this to the next corner counterclockwise. So the operation sigma can be written as this: 1 goes to 2, 2 goes to 3, and 3 goes to 1. That's basically it. This is what the operation do. So if you repeat the operation, if you did 2 times, you're going to rotate it 2 times. If you repeat it 3 times, you're going to just get back to the first place. So sigma to the power of 3 is equal to E. Why? Because we defined E to be the no rotation. It's the unit element. If you don't rotate any times, if you don't rotate any times, it's going to stay at the same place. So it's a unit element. It doesn't change a thing. And if you don't rotate any times and then rotate 2 times, it's the same as rotating 2 times. Or if you rotate 2 times and then don't rotate, it's the same thing as rotating 2 times. It's pretty damn easy to say. But we call it is a group, but let's check if it is a group. Okay. Does it has law of composition, or in other words, is it closed under operation? Doesn't go out of the group of the set that we define it? Yeah, it's just rotation. It can't do much. Is it associative? Yeah. If I rotate 1 time and then 2, or if I rotate 2 and then 1, is it the same? Yeah, basically, it's the same thing. Rotate this 1 time, and then rotate 2. Rotate 2 and then rotate 1. You're going to see the same shit. Does it have E? Yeah, and we defined it to be the just don't rotate it. I'm calling the association rotations because it's easier to see. But yeah, it has the unit element. Okay. This is basically saying that there is an inverse. It does. If you rotate 1 time, just rotate 2. If you rotate 2, just rotate 3. And for every 4 or 5 rotations, just divide by 3 and take the integer or something like that. I don't remember how you do it, but it's pretty easy to see. If you rotate like 5 times, it's the same as rotating 3 plus 2, which is the same as rotating 2 because sigma to the power of 3 is E, and it doesn't change a thing. What's interesting about studying finite cyclic groups, you're going to ask me? Well, in my opinion, it's cool. It's just that it's cool and it's interesting. There isn't much we can say about this because I already explained it everything. So let's see another operation here. Well, what happens if we define a symmetry on this group? What's going to happen? Nothing. You can define the symmetry. Actually do that yourself. Define another 2 operations, 3 operations actually. It's going to be the symmetry on each corner, and then check how many subgroup it has. You're going to find something pretty cool, I guess. I mean, if you're not that dumb, you're going to find it anyway.